Good afternoon, everyone, and welcome to the Verisign Labs Distinguished Speaker Series. My name is Bert Kaliski. I'm the Chief Technology Officer at Verisign, and we're so pleased to have you here with us today. This is the first time we've had one of our Distinguished Speaker Series outside the United States, outside our headquarters, and to have it here in Fribourg in Switzerland is just a delightful indication of our commitment to the best operations and the best talent all over the world. We're grateful for the presence that we have here. Domain names. People start with some spoken understanding of what they're looking for. How do you make a name that makes sense to them so they can navigate confidently? So, Professor Hennebert.
Thank you, Bert, for this introduction and for the opportunity to present our research, and in partnership with Verisign, we will present today what we do in phonetic domain name research. Let me start with a nice picture of Fribourg. This is our city, and as you can see, we have a wonderful new bridge that we will be able to use in some months now. It's going to be open, and as you can see, Switzerland is a very nice country, right? And Fribourg is really at the middle of Switzerland. It's at the intersection of linguistic regions. At the left side of this bridge starts the German-speaking region that extends to the rest of Switzerland in the German part, and then Austria, and then Germany with about 80 million people speaking German. On the right side, you have French-speaking region going to Lausanne, Geneva, and then France, a part of Belgium where I'm coming from. And then it's also about 80 million people. And then if you go across the mountain, about 100 kilometers, not so far, start the Italian region with about 60 million people speaking another language. And in Fribourg, we have this chance to be at the intersection of all these regions. And then it makes sense for us to play with languages because we like it, and it's our daily life, right? So let me start with my talk. It's going to be about International Domain Phonetics. So it's a project that is done in close collaboration with Verisign. This is the team members over there. I'm the first one by alphabetical order, but I give all the credits to the other one that have been bringing all the ideas and the work, actually. I'm just entertaining you today. So let me start with a little movie, and I will ask you to pay attention to what this wonderful lady is going to be telling you. It's a YouTube movie. You can find it on YouTube. Just pay attention to what she's saying, right?
Bonsoir. Chaque heure le bulesson sa voix de 4 dents. Che le buono tuoso gioschi monard, je le podimo. Mangiorno pratti solla viretto putta pesca madra solla. Português que forma choice redetsaio al merianto. Grammar hauda faduro ki sanchere u padresa me. I'd say I kill it in my bones. Dumb things in it. It's like a miraculously mobilizing felt tip pen, like a ordinary sentence of a marinating follow. Chimisi na tatturu yukimas. Yukitura basanchito yuski di matoska. Masakitoro yukimekte. La maniera casual mató a mierda, que tondo quise el solo un lugar abierta per viva con todo conmigo pueses. A huevo cabrón. Yeah, I mean, Trevor misgendered appearing like Monin Fair. Follow me, like a pending French racket, Bologna value precisely. Hello? Dapat si Dima, pedep milkar babaji pani mereka adiamal magar jaunga. Vedi kita miliki me bariba. مقولوس الواحد على الحباب ما يعرق التحدي من أصل يشتقط لي يعرفهم خلاص أنا أدرس اللغة العربية في البيت.
So, maybe you speak some of the languages that have been presented. Did you understand what this lady said? No, right? But still, it sounds like the language, is it? How does she make it? Do you have an idea? Is she using random sequences of phonemes? Yeah, maybe in the target language, but actually it's not really random, right? It has some structure, right? If she would be taking random sequence of phonemes, it would sound quite strange. But in machine learning, we say she's using patterns of sequences of phonemes And this is exactly what we are going to exploit. If we can find nice technologies to spot these patterns, maybe we will be able to play with it to build product or nice business cases. Let me convince you that these patterns do exist. This is a kind of file we play with in this project. It's called dictionary files. So on the left side, you see words, okay? And on the right side, you see sequences of symbols that represent the phonemes, the sounds that correspond to the word that are on the left part. And as you can see, the file is pretty big, right? It has a lot of input, a lot of data in it. Let's have a look. It's a US English dictionary file, so it's about 200,000 names, common names, a bit of family names, and so on, but not all names. This is a problem for us, as you will see. And then let's try to find these patterns, right? Let's take, for example, a sign, like in Verisign, okay? And then sign appears in a lot of words, as you can see. Web designer, 99 design, and so on. And then if we look at sign, we can spot on the right side that you have a sequence of phoneme that correspond to this little part of word, as we say, okay? D, A, big I, N, these are symbols representing phonetic sound in International Phonetic Alphabet. And let's find another pattern. And I'm looking in this file, and you see we find this pattern, resigning, resign, and so on, unresign, resignedness. And this pattern comes again and again and again. So if we could build, and this is actually what we did, if we built a technology to spot these patterns and to play with it to do things, okay? So we have two questions, one which is scientific, one which is business. From a scientific point of view, can we automatically discover such phonetic structures? The answer is yes. And the second question, can we use this information to enhance web experience? And this is very interesting in some domains, like, for example, domain name suggestions. So let's imagine we have this technology. So I'm willing to book or to buy a domain name airmix.com. Of course, airmix.com is already taken because it's a bit busy. And then the system will be able to automatically suggest closely sounding domain name. So if I'm looking for airmix, maybe the system will propose airmix with a R and mix, airmix with a CS at the end, airnix, which is closely related phonetically, and so on. So there is a clear interest in this to suggest in a new way domain names for web users. So the question from a scientific point of view, I'm not going to be very technical, but I will give you a hint on how we do this. We have different challenges. The first one is to transform any input into sequence of phoneme, even family name, even company names, even names you invent. So these inputs we don't find in our dictionary. So we need to generalize. That's the first challenge. Then we need to spot the phonetic patterns, as I have shown you just before. And then we need to replace the patterns with similar sounding ones. And then we need to go back into the graphemic world to translate back into a sequence of characters. Okay, so we came with this processing chain that I will show you in a few minutes. But Verisign came with other constraints, like we need to scale to as many languages as possible. So if we find a good technology for French and it takes 6 more months to build it for German, then it's not very useful. So we need to scale to as many languages as possible, and we need to be efficient as well because we target to have a real use of what we do. So this is a processing chain. We have actually 3 parts. I'm just going to give you a little bit of hints about how it's working on the first part. So we have a G2P grapheme to phoneme mapper that will map any word into a sequence of phoneme. Then we have a P2P phoneme to phoneme mapper that will bring some alterations. And then we have a P2G to go back to graphemic representations. So let me just focus on the first building block so you understand a bit how we do it. We actually build index of correspondence between grapheme and phonemes looking at the context of the grapheme. So for example, if I take the letter I, isolated, I will be mapped to phoneme E, like in pixel. but E is not good for air mix, as you can hear it, right? So we need to look a little bit more of context. So let's take a letter on the left. AI is still not good for air mix, but it's mapped to, in some other words, to I, like in gain or vein, okay? The right context for us is 3 letters. So there we know that air is mapped to a special phoneme that is written with a little star, which means R, okay, R mix, like in R mix. So the technology we built is able to look at the context of a single character, looking left, right, left, right, left, right, building context, enlarging context, until we find the right correspondence in the phonetic domain. And then we store this correspondence in an efficient way, in an efficient data structure, using trees. Why trees? Because lookup in trees are very efficient, right? We can build very fast technology in terms of algorithmics. So I'm not going into details, but we build a tree. At the top of the tree, we have the basic correspondence between grapheme and phoneme. The downer in the tree, the more specific we are, the more exceptional we are in the way we pronounce sound. So we go in the tree looking left context, right context, left context, and so on. So for example, you have the I of air mix, we look at the M and the I, and so on. And then at the bottom of the tree, we find the right correspondence. We have a pre-processing step. I'm not going into detail, but we use other kind of algorithms. It's quite complex at some point. We need a pre-processing step to align the grapheme string and the phonetic sequence in the right manner. So this is the output of this pre-processing step. We use hidden Markov models, kind of complex statistical model to do this, but we could make it. And then we are then able to build the tree that I just presented before. So the central idea of the technology we have put together in this project is to solve the mapping problem between grapheme and phoneme and the indexing problem using a very efficient tree-based lookup. And then I'm not going to explain P2P and P2G because it's a kind of similar way of doing things. It's a reverse problem for the P2G. And actually, the P2P comes as a byproduct of the lookup, and we exploit the structure of the tree to find alteration of the phonetic correspondence. So what can we do else? So you know now that we can do similar sounding domain name suggestion. That's one business case. Another business case could be brand protection. So let's assume I'm the owner of perfume.com, for example. The system is able to suggest a similar sounding domain name, so we can protect our brand, which is a very important matter for companies. And we could, for example, registering similar sounding domains to cover a potential phonetic misspelling and so on. Something else we can do with the technology is to mix languages. For example, if we use the dictionary of German speaking for the first part and English speaking for the last part, we can answer questions like this one. We can mix language. For example, I'm speaking about Der Spiegel, which is a famous magazine in Deutschland, in Germany. And then an English-speaking person is listening to me. And how would he write it phonetically? This is the question. By mixing languages like this in our processing chain, we can answer questions like this. So I am German. I would like to know what are the potential phonetic spelling of my domain by native or non-native users, so that I can, again, do brand coverage, but in an international perspective, if you want. Okay? And I can catch up maybe important part of network traffic doing this. Next business case is what we call Latinization of names. So, for example, people in Russia, they use Cyrillic characters, and maybe for international reason or for other reason, they would like to have a kind of transliteration of their representation into the characters of another language, like, for example, Latin character here. And then the technology is also able to do this, so it's kind of also important use case of the technology. Yeah, to come back to our nice lady, right? We could also simply browsing the tree, generating jumps randomly, respecting the probabilities of going left or right in the tree, and so on, and then generate potentially good sounding domain names. So we constrain, for example, a length of 6 characters, or 7, or 8, whatever, and then the system is able to generate thousands and thousands and thousands of potentially good sounding domain names. So this is an output of the system with a length of 6. As you can see, it's sounding quite okay, right? It sounds like English words, isn't it? Well, maybe not all.
When Google didn't exist, it was crazy.
Yeah, exactly. Yeah. So Google is a good example. I will show you some example with a name Google just after. So the technology we built together with Verisign is ported on different languages. We cover now English, French, German, Spanish, Portuguese, Italian, Russian. And then we are hitting a bit of more difficult languages for different reasons. Turkish, Korean, Japanese, Hindi, Arabic, and Chinese are under work. Some language we know already we will have a lot of difficulty. Some other languages that are in the list we will probably find solutions. They are just more difficult because, for example, Chinese is a tonal language, and they have an ideogram representation of the string, which makes our technology is not scalable to this kind of representation. Arabic is a bit strange as well because they don't pronounce vowels. They don't write it. They pronounce it. They don't write it. So in the grapheme representation, we don't have the vowels, which makes it difficult for our technology. We need a pre-processing step to handle this and so on. So I'm at the end of my presentation. So I'm playing a bit with technology to write you this slide. The project is supported by the Commission for Technology and Innovation. So the CTI, which is almost fully funding the academic part of this project. And of course, we have the support of Verisign internally for building this very nice project. So while you will maybe ask me some question, I will play the little demonstration of our tool. Yeah, I just need to launch the. Maybe we can watch together the first few examples. So basically, we have the phonetizer part, the graphetizer part, which are the two blocks where we can choose the languages. We choose a target language for the phonetizer, target language for the graphetizer. We input a grapheme. We have some options, but we just use the standard thing. You see the computation is very fast. It's less than 2 milliseconds to get the answer. The trees are really efficient. And then you see I have put Verisign. You have some suggestions, alternate suggestion for Verisign. I think it sounds good, right? It's quite close. Let's try with Fribourg. Okay. So Fribourg. Fribourg. It sounds. If I would build an alternate site about underground Fribourg, I would maybe look at this pronunciation. That would be nice. And then, yeah, let's try with famous Google. Let's see what we get. Of course, you can do brand protection targeted on specific sequence of phonemes. So I just click on the first line to get specific on a sequence of phoneme. And this is what we get. We get the first one, which is a good sign that we find back the right pronunciation. So the system regenerates the initial input. But then we have a very nice, I think, suggestion for in a brand protection case. And then we can mix languages, as I said, with Spiegel. Just give you another example. So we have German speaking and target in US English. And then Spiegel, as we hear the sh of the German-speaking guy in the grapheme suggestion. So,
thank you very much.
Thank you.
That was very well done, and that is about where good domain names come from, among other things.